This is a new concept in double integration. Remember, we are not doing this only for a course in maths, because the students of engineering or science generally encounter these problems in some of their problems in core subjects. So they'll have to come across some integrals, let us say a probability integral or an integral that occurs in other contexts. So the idea is to evaluate it, and in the process of evaluation, you generally land into some tricky situations. One of the situations is where the original integral has got a sort of mismatch of the region with the limits, in the sense that the limits are all fine, but the region is not favorable to make the process of integration is easy. Now, one of the things we always talk about is in tough situations when the problem cannot be resolved in the original domain, you think of changing it, changing the variables so that you are recreating the problem in a new domain. So it should not be mistaken that the new domain can also be a Cartesian framework, but in the process of changing the domain, certain good things may happen. One of them is reshaping of the region. For example, I've got a very bad region in the original problem. I can reshape it into a very simple region which can be handled and analyzed easily. Case 2, the region may be all right, but it may be a figure or a region that is in bad orientation. So if I can relocate that same region into a more friendly reference frame, then my problem becomes easy. So I've explained why this technique is becoming important. It becomes necessary when the region and the integration don't go together properly. So my whole idea is to simplify by either reorienting the figure or to reshape the figure. That's the point. So all this will look very nice, but unless we actually see it in practice, we will not be able to understand completely. So let me take a few problems. But before that, let me write the context. The context is unfriendly region with respect to the integration process. What action can we take? Create the problem in a new domain by introducing new variables. What happens? What happens when you change the variables? As I told you, there will be two possibilities. Reorientation of the region, or it can also be reshaping of the region. Normally, reshaping of the region is a very advanced technique that is many times seen in mathematical morphology also. But this is not the context where we talk about morphology. But morphing essentially is the same. You reshape generally. Okay. So let me take up a couple of illustrations and tell you how we go about this business. And in this process, please don't forget, whenever you introduce new variables, it is a natural process to determine what is known as the Jacobian of the transformation. So I'll explain through my examples. Taken a problem where I'll explain this concept. This problem has got some difficulty. You can sense it now. The function is not so good to look at. Okay, and imagine you are integrating with respect to y, where the variable y is sitting in two places and it's an exponential function. So we can't imagine how to begin the integration confidently. So what I do is I will show you how to change the variables in this problem. So how do I begin my process? Change of variable means I want to change my domain itself. So for domain change, I require a pair of equations which will transform the original variables x and y to two new variables, let us say u and v. So how do I sense that and how do I make it happen? So what I do is I'll go to the region where some unfriendly term is there. That is where I begin my thinking process. So I'll replace that x plus y with u. And to minimize the complication, I will make just this y as v. Or let me put it the other way around. Okay. This is the same as v is equal to y. So I replace x plus y with u and I replaced y with v. So this is where I find what is known as the Jacobian of the transform. Suppose I am writing the Jacobian of the variables u and v with respect to x and y. It's a determinant with the partial derivatives of u in the first row and the partial derivatives of v in the second row. U with respect to x, u with respect to y, arrange it to the first row. V with respect to x, v with respect to y, arrange it to the second row. But these four quantities have to be determined from these equations. Let's fill up these plots. Differentiate u partially with respect to x, you get 1. Differentiate u partially with respect to y, you again get a 1 because x is a constant and it vanishes. V with respect to x, the derivative is 0 because there is no x at all, and v with respect to y is 1. So what does this give us? This gives us a number. So the Jacobian is 1. So what does it mean? It means the area element du dv is Jacobian times dx dy. So the UVs get transformed to xy through this process, and this is my relation between the area elements. So du dv is 1 times dx dy. Now be careful, sometimes the Jacobian can be negative, but you should take its absolute value because we are trying to relate to area elements. Area cannot be negative, so therefore we always use a modulus there. But how I'm going to use this knowledge? The knowledge is to replace dx dy in the original problem, dx dy or dy dx, with du dv. So I will get some new integral in the variables u and v. But many things will have to be achieved now. First thing is, what is the new region? What was the original region first of all? What is the new region? In the new region, how does it look like? How do I fix my limits? These are all the situations to be understood. So what we have to do is go back to the original problem, look at the limits. Inner limits are functions of x. So therefore, from here, we understand it's an Rx region with x is equal to 0 to x is equal to 1, x is equal to 0 to x is equal to 1, y is equal to 0 to y is equal to 1 minus x. Y is equal to 1 minus x. So let me look at this region. X is equal to 0 to x is equal to 1 looks like this. Y is equal to 0 to y is equal to 1 minus x. Y is equal to 1 minus x is the same as x plus y is equal to 1. So therefore, it must look something like this. So this is x plus y is equal to 1. These are the vertices, and this is the region of integration. So if you look at the problem so far, there is nothing much in the region, but there is something complicated about the function. This problem cannot be easily solved even by changing the order of integration. So I am now teaching through this example how a change of domain, change of variables can help the evaluation process. So now I'll have to explain things. How does this diagram get transformed to a new diagram in the UV plane? Alright, so I'll keep my UV plane ready. So corresponding to x is equal to 0, I'll just write mappings. Corresponding to x is equal to 0, I'll go and search these two equations. X is present here. When I put x is equal to 0 here, I'll get u is equal to y. X is equal to 0 gives me u is equal to y. Let me go to y is equal to 0. Y is equal to 0 produces. So I've got two options. I can go here, I'll get u is equal to x. I'll go here, I'll get v is equal to 0. That's a better one for me. So I'll have two options here. I'll have u is equal to x or v is equal to 0. Then let me go to x is equal to 1. X is equal to 1 produces u is equal to 1 plus y. There's no chance of entering this equation because I don't see x at all. Then I go to x plus y is equal to 1. That gives me straight away u is equal to 1. So now it's a confusing compilation, but I will select whatever is very friendly for us. So I'll select, let us say u is equal to 1. I'll select v is equal to 0. Then what about the rest? How do I manage to pick up? Because I want a region that is bounded. So when you have the uncovered equations, let us say u is equal to y and u is equal to 1 plus y and u is equal to x still in hand, how do I get it? So I will drop this u is equal to x because I've chosen v is equal to 0, and then there's no confusion about this, so this is accepted already. So let me put it on the graph paper. V is equal to 0 is this axis, and then I have u is equal to 1, which is that. Then I need something that will make the region complete. I'm going to explain how that can be done. Okay. All right. Now we need one more curve or line to complete the region. Right. So let's pick up this u is equal to y. Let's go to v is equal to y. Y should be eliminated because we are in the UV domain, no interference of x and y. So when u is equal to y and v is equal to y, u is equal to y and v is equal to y together produce u is equal to v or v is equal to u. So v is equal to u is a straight line through the origin. This is your v is equal to u. This is 1, 1. This is 1, 0. This is 0, 0. And then this is the region of integration in the new domain. Now what do you find? Where is the original situation and where is this? So you can see that a right triangle there has been transformed to another right triangle here. But does it have an impact on the solution? The answer is yes. Because the original one definitely was an untouchable problem. So it's going to change now. So we will have to write this region just the way we used to write Rx, Ry. So I'll call it an RU region with u is equal to 0, u is equal to 1 as the vertical lines or vertical boundaries. V is equal to 0 will form the lower boundary and v is equal to u will form the upper boundary. So this term will help us to transform this double integral into a new double integral. And when it transforms, how does it look like? 0 to 1, 0 to 1 minus x, e raised to y upon x plus y dy dx corresponds to u is equal to 0 to 1, v is equal to 0 to u, e raised to, replace y with v and replace x plus y with u. What about dx dy? Dx dy is replaced with du dv. In this case, the order is dv du because these are the limits. So this is what we'll have to evaluate now. And let me show you that. It's a very simple one, but some of you may get confused. Let me copy the right hand side for you and then evaluate. Integral 0 to 1, integral 0 to u, e raised to v by u, dv du, because these are the limits for v. So don't get scared. The integration of e for v by u with respect to v would be e power v upon u divided by the coefficient of v, which is 1 upon u. 0 to u du. So just do that. Now in place of v, you substitute the upper and lower limits. So I get e power u upon u minus e raised to 0. So this will be 0 to 1 u times e minus 1. You can extract this outside so that it does not hinder the process. The integration of u would be u square upon 2, 0 to 1. So this would be e minus 1 into half. So that gives the output half times e minus 1. So look at the types of experiences we are going through. There are those straightforward problems that you can evaluate without any hassles, but there are problems where you have to change the order of integration, dy to dx or dx to dy, or sometimes you have to go for region splitting and all that. Now comes this technique which allows you to evaluate certain complicated problems, but not in the original domain, in a transform domain. The moment you transform, the concept of Jacobian enters. So some bit of experience we gained through this problem. Let us see what the next problem teaches us.